Yeah, hello everyone. Today we will discuss fourth video of fluid mechanics unit number 5, that is flow through pipes. Okay. In this we discuss about dimensionless numbers. The significant, important dimensionless numbers used in the analysis of various fluid flow problems, used in analysis of real world engineering fluid flow problems, okay, in a fluid mechanics sciences. So in this, the first number is Reynolds number. Reynolds number is the ratio of inertia forces of a fluid to the viscous forces in the fluid. Okay, inertia forces to the viscous forces. So this number actually compares the importance of inertia force with respect to the viscous force. Okay, now as this is a ratio of the two forces, so it doesn't have any unit, so it becomes dimensionless. Okay, inertia force can be written as mass into acceleration of the flowing fluid. Now this is written as per Newton's second law of motion, mass into acceleration of the fluid. Further, mass can be written as density of the fluid into volume of the fluid, that is the mass of the fluid, multiplied by acceleration can be written as velocity per unit time, as you see here. Velocity per unit time is acceleration, change in velocity per unit time. Further, we can manipulate like time can be taken below volume, so this is volume flow rate, discharge rate, and this can be written, discharge rate can be written as area into velocity, cross sectional area of a flow passage into velocity. So this is the manipulation regarding the various parameters. So further we get the formula of a rho a v square. So this is the formula for inertia force, rho a v square, okay, observed in the fluids. Viscous force Fv can be written as, expressed as shear stress present in the fluid due to the viscosity multiplied by tangential surface area of the fluid layers. Okay, this is a tangential surface area present in the fluid layers. So shear stress is a tangential one into tangential area. So this gives you viscous force. Further, shear stress can be expressed as mu into du by dy. So this is as per Newton's law of viscosity, tau equal to mu du by dy into area. Du by dy can be written as v by L. Okay, this is a velocity gradient, so velocity per unit length. So you have mu into v by L into a. Thus Reynolds number can be written as inertia force to the viscous force. So numerator is rho a v square upon mu v by L into a. Okay, so further simplification results in a formula, Reynolds number is equal to rho VL upon mu, as you see here, rho VL upon mu. This can be expressed further as VL upon nu. So here rho VL upon mu, mu is dynamic viscosity. In this second formula, nu is kinematic viscosity. Rho is the mass density of fluid, capital V is average velocity of fluid, L is the characteristic dimension of the flow passage. For a pipe flow, characteristic dimension is nothing but diameter of a pipe. L is characteristic dimension, characteristic length. Okay, so Reynolds number is finally written as VL upon mu or rho VL upon mu. So it is important in study of pipe flows. As we know, we classify laminar, and turbulent flows with the help of Reynolds number. Also, it is important in the flows of a completely submerged bodies like the submarines and the aeroplanes and the cars which move in the atmosphere. So, analysis of these fluid mechanic problems is done with the help of Reynolds number. Second formula, second important dimensionless number is Froude's number. It is a ratio of it is the square root of the ratio of inertia force to the gravity force in a fluid. Okay, inertia by gravity force, root of this square root. Inertia force is already expressed as rho a v square. Gravity force is nothing but it is the weight of the fluid mass. So weight is equal to mass into acceleration due to gravity. Mass is density into volume into g. Volume can be written as area into length. Okay, these are primary dimensions. So rho into a into l into g. Okay. Therefore, put here Froude's number is equal to root of rho a v square as the inertia force divided by rho a l g as the gravity force. Then simplify this, rho a cancels out. So therefore, Froude number is equal to, and take the root. So it is numerator is capital V upon root of L into G, or capital V upon root of GL. Now remember, Froude's number is also dimensionless number, one of the important dimensionless term, and it is important in analysis of open surface flows. Okay, the flows of the fluid which are open to the atmosphere, non-closed type of fluids, where gravity forces are important in such a fluid flow situations. Third important dimensionless number is Euler's number. Euler's number is a square root of ratio of inertia force to the pressure force in the fluid. Pressure force can be written as intensity of pressure multiplied by area. Intensity of pressure multiplied by normal area, that gives you pressure force. So substituting here Euler's number as square root of inertia force rho a v square upon pressure intensity into area, then cancelling the area and bringing the density below the pressure. So v square upon p by rho, and taking the root you get capital V upon root of p by rho as a Euler's number. Also there is another formula of a Euler's number, that is delta p upon 1/2 rho v square. So both of these two formulae are correct as far as Euler's number is concerned. Both are right. Okay. Euler's number is important in case of studies of cavitation. Cavitation studies where pressure forces are predominant, and those are important in such situations. Fourth dimensionless number is Weber's number. Weber's number represented by WE. It is again defined as square root of the ratio of a inertia force to the surface tension force present in the fluid. As usual, inertia force is rho a v square. Let us write this area as a length square. So length into length is area. So rho L square v square. Surface tension force Fs can be written as the property surface tension sigma multiplied by length, because we know surface tension sigma is nothing but its unit is Newton per meter. So surface tension force per unit length multiplying by length, sigma into L. So unit is Newton here. This will be Newton. So Weber's number is square root of rho L square v square upon sigma L. Cancelling the length, and rearranging these terms as velocity per unit root of sigma upon rho L, taking the square root. Also, there is one more formula of a Weber's number as rho v square L upon sigma. So this formula is applicable for liquids. So this is liquid Weber's number, okay, for liquids. So this Weber's number is important in thin films of fluid, where the liquid has a very thin film and a flow takes place, or the cases where the depths of the flows are very small, like a flow of a sheet of the fluid, shallow depths of the flow. Okay, the examples can be thin film fluids are like droplets, then capillary flows, and the sprays of the fluid. Okay, in those analysis, Weber's number is important. Next one is important number as a Mach number. So Mach number is again defined as square root of the ratio of inertia to the elastic force of a fluid. Okay, elastic force in a fluid is because of property bulk modulus of elasticity, that is also known as elastic stress, capital K. So this capital K multiplied by area gives you elastic force. Capital K is bulk modulus of elasticity into A. Area can be written as in terms of primary dimensions as a length square, so A into L square. So therefore Mach number can be written as square root of rho A V square upon K L square. Okay, substituting area as L square, so L square cancels out. So this is square root of V square upon K divided by rho. Taking the root, so we have finally velocity V divided by root of K by rho. So this is nothing but capital V by capital C, where numerator is capital V. Capital V means it is the velocity of the flowing fluid, and capital C denominator is nothing but it is the velocity of sound in a given fluid at a given conditions, at a given temperatures. So velocity of sound is nothing but root of bulk modulus of the fluid divided by density of the fluid at the given conditions, okay, given temperature and pressure. So Mach number is a very famous number. It is a ratio of velocity of a fluid per unit velocity of a sound in a given fluid at a given conditions. Remember, Mach number is important in the studies of aerodynamics and water hammer phenomenons. Okay, so it has a relative comparison of a velocity of fluid per unit velocity of sound. You can see if a Mach number is more than 1, then the flow is classified as supersonic flow. Supersonic means the flow velocities, the fluid flow velocities capital V are more than velocity of the sound in a given fluid at the given conditions. If Mach number is less than 1, so capital V is less than C, it is termed as subsonic flow. If the Mach number is equal to 1, it means the velocity of fluid is equal to velocity of sound. It can be called as sonic flow. And likewise, if a Mach number is much more than 1, typically it is more than 6, okay, it's more than 6, it is classified as hypersonic flow, sometimes 8, hypersonic flow, where velocities of fluid is much more than the velocity of sound in a given fluid. A higher Mach number signifies the predominance of the effect of compressibility of the fluids. Okay, so Mach number is important wherein the fluid gets compressed, or compression of the fluid is observed. For example, all the applications of aerodynamic sciences, Mach number is very very important. So this completes our unit number 5, flow through pipes. Okay, thank you.